A storm formed in April. The Pacific barely wakes up that early. 48 hours later, it had winds of 185 miles per hour. It wiped out power for 50,000 Americans on islands most people couldn't find on a map. And scientists say that storm was just the opening act. The ocean underneath it is running at near-record temperatures. A pulse of heat the size of a continent is moving toward the surface. El Niño is coming faster than anyone expected. We're going to cover what's heating up, what's already broken, and what's about to get far worse. If you find this useful, a like and subscribe helps more people hear it. Let's go. Something was wrong with the Pacific before 2026 even started. Normally, after a major El Niño ends, the ocean cools down, the heat disperses, temperatures drop back toward average, the system resets. That's how it has worked for as long as scientists have been measuring it. That reset never happened. The El Niño of 2023 and 2024 was powerful. It pushed global temperatures to levels never recorded in human history. Coral reefs cooked, fisheries collapsed, weather systems across 6 continents went sideways, and then, technically, it ended. La Niña conditions returned. Scientists expected the Pacific to exhale. The Pacific didn't exhale. By January 2026, ocean temperatures around the island of Tonga were 3 to 4 degrees above normal. 3 to 4 degrees sounds small. Stretch that temperature difference across hundreds of miles of open ocean, and you have something more like a slow-motion disaster. Marine heatwave alerts went out for Tonga, Fiji, and the surrounding island chains. These alerts described conditions normally associated with the peak of a strong El Niño event. La Niña was still technically on the books. Reports came in from Tonga of fish dying in the water. Mass deaths. Species that had survived in those waters for generations were dying because the ocean around them had become too warm to support them. And this was January. Storm season hadn't started. El Niño hadn't arrived. The Pacific was doing this on its own. There's a reason for that, and it matters. Every El Niño leaves behind a warmer ocean than the one it found. Climate change has been raising baseline ocean temperatures for decades. So when the 2023 to 2024 El Niño ended, it didn't leave behind a normal Pacific. It left behind an already warm Pacific, sitting on top of an ocean that had been heating up for a century. The starting line for 2026 was higher than any starting line in recorded history. Think of it like a fever that never fully breaks. Your temperature drops from 104 to 101. Technically better, still dangerous. By April 2026, the Copernicus Climate Change Service confirmed that global sea surface temperatures across extrapolar oceans had reached approximately 21 degrees Celsius. That made April 2026 the second hottest April ever recorded for ocean surfaces, sitting just below the all-time record set during the peak of the 2024 El Niño. Samantha Burgess, the climate lead at the European Centre for Medium-Range Weather Forecasts, made a public statement on May 7th. She said it was a matter of days before the ocean broke all-time records again. Days. A team at Mercator Ocean International confirmed in May that marine heat waves across the Northwest Pacific were holding at moderate to locally extreme levels. Off the coast of Central America, severe heat waves were expanding and intensifying. The ocean was not cooling, it was building. For a teenager sitting anywhere near a Pacific coastline, this is the part where you should pay attention. The warmth driving everything that happens in this story already existed before the storms formed. Before El Niño declared, before any forecast was issued, the system was already loaded, and underneath all of that surface heat something was moving, something scientists were struggling to find words for, a pulse of water carrying temperatures 6 to 7 degrees above normal, travelling hundreds of feet below the surface, crossing the entire Pacific basin. It hadn't reached the surface yet. When it did, everything would change. The number that stopped climate scientists in their tracks arrived quietly. April 2026. Global average sea surface temperature across extrapolar oceans, 21 degrees Celsius. Second highest ever recorded for any April in history. The all-time April record was set just 2 years earlier, during the peak of the strongest El Niño in recent memory. April 2026 came within a fraction of matching it, and this time, El Niño hadn't even officially started yet. That's the detail that matters. Every time scientists have seen ocean temperatures this high, there was a full El Niño actively pumping heat into the system. April 2026 produced near-record ocean heat during what was technically a neutral or La Niña period. The ocean achieved something it had never achieved before without that extra push. Samantha Burgess, the climate lead at the European Centre for Medium-Range Weather Forecasts, put it plainly. She said ocean temperatures were days away from breaking all-time records again. Her team's projections showed that by autumn 2026, Central Pacific Ocean temperatures could rise by up to 3 degrees above normal. 3 additional degrees on top of a baseline that was already near the hottest in recorded history. To understand what that means, picture a pot of water on a stove. The burner has been on low for 100 years. Someone just turned it to high. The warmth was showing up in strange places and at strange times. Sea surface temperatures near Fiji and the surrounding island chains in January 2026 were 2 to 3 degrees above normal. That's the level of warmth that typically only appears at the peak of a strong El Niño. It appeared during what was supposed to be the recovery phase. While the system was supposedly cooling down, scientists track something called a marine heat wave. It's exactly what it sounds like, a region of ocean where temperatures run significantly above normal for an extended period. By May 2026, the Northwest Pacific was holding marine heat waves at moderate to locally extreme levels. Off Central America, severe marine heat waves were expanding westward, pushing into open ocean regions that had rarely seen conditions like that before. The pattern wasn't random. Ocean heat doesn't pile up by accident. It builds through a combination of forces: long-term climate change raising the floor, weakened wind patterns that allow surface water to hold warmth instead of mixing it down, and the positioning of the ocean currents that either trap or release heat. In 2026, all 3 of those forces were pointing in the same direction. Here is why that matters on a personal level. Hurricanes and typhoons are heat engines. They pull energy directly from the ocean surface. The warmer that surface is, the more fuel the engine has, and in 2026 the fuel supply was nearly unlimited. Every degree of extra ocean warmth translates into stronger storms, faster intensification, and more rain. The relationship is direct and confirmed. Scientists have measured it across decades of storm data. April's record heat wasn't an abstract statistic. It was fuel being loaded into a system that was about to ignite. The European Centre's projections for autumn 2026 were already alarming forecasters across the Pacific. If Central Pacific temperatures rose by 3 degrees above normal during peak storm season, the results would be unlike anything the modern world had experienced. And beneath all that surface heat, the real driver of 2026's story was still invisible, still moving, still building toward the surface from hundreds of feet below. Something was coming up from the deep, and it had been described by the people tracking it as possibly the strongest of its kind ever recorded. Hundreds of feet below the surface of the equatorial Pacific, something enormous was moving east. You couldn't see it from a ship, you couldn't feel it from the shore, satellites couldn't photograph it directly. Scientists only knew it was there because of a network of underwater sensors called Argo floats, drifting through the deep ocean and transmitting temperature data back to research teams. And in early April 2026, those sensors told a story that stunned the people reading them. A Kelvin wave was crossing the Pacific. A Kelvin wave is a pulse of warm water that travels along the equator, deep below the surface, moving from west to east. It's not a wave you can surf. It moves slowly, maybe a few miles per hour, and it spans thousands of miles from side to side. What it carries is heat. Enormous amounts of heat, compressed into the layer of ocean between about 300 and 800 feet deep. This particular wave was carrying temperature readings 6 to 7 degrees above normal. Forecasters at Climate Impact Company reviewed the data and stated publicly that this was possibly the strongest Kelvin wave ever recorded. 6 to 7 degrees above normal in the deep ocean. To put that in perspective, a 2-degree rise in surface ocean temperatures is enough to fuel a Category 5 hurricane. This wave was carrying 3 times that amount of extra heat, and it hadn't even reached the surface yet. Think of it like a massive underground pipeline of hot water running beneath the entire Pacific Ocean, thousands of miles long, hundreds of feet down, moving east. And the nozzle at the end of that pipeline was pointed directly at the coast of South America. When a Kelvin wave reaches the eastern Pacific, something specific happens. Cold water normally rises from the deep ocean off the coasts of Ecuador and Peru, a process called upwelling. That cold water keeps the eastern Pacific cool and suppresses storm formation. When the Kelvin wave arrives, its warm water suppresses that upwelling. The cold water stops rising, surface temperatures spike, and El Niño begins. In early April 2026, the Kelvin wave east of the international dateline was already carrying those 6 to 7 degree anomalies. Climate analyst Scott Yuknis compared the pattern of upper ocean heat in the first months of 2026 to the patterns seen at the start of two specific years, 1997 and 2015. Both of those years produced the strongest El Niño events ever recorded. As of mid-April 2026, the surface of the eastern Pacific was technically still neutral. The index scientists used to measure El Niño strength, called the Niño 3.4 index, sat at just plus 0.2 degrees, barely above zero. But the subsurface was behaving as if El Niño had already fully arrived. The heat was there, it just hadn't surfaced yet. Forecasters described it as a gun that was already cocked. And here's the thing about Kelvin waves that makes them so consequential. Once one of this size is moving, it can't be stopped. It doesn't dissipate. It travels east until it hits the coast and releases its energy into the surface ocean. The process was already underway in April 2026. The arrival was a matter of when, not if. Scientists were watching the sensors. The numbers kept rising. The wave kept moving. What happens when 6 to 7 degrees of subsurface heat finally surfaces across the eastern Pacific is a question that leads directly to El Niño itself. And understanding El Niño requires understanding something most people get wrong about it. Most people have heard the name. Almost nobody knows what it actually does to the ocean. El Niño sounds like a weather event that just makes things a little warmer somewhere. Drier summers, wetter winters, slightly unusual temperatures. The reality is a complete reorganization of how the entire Pacific Ocean moves. And once you understand the mechanics, the size of what's coming in 2026 becomes genuinely frightening. Start with the trade winds. Under normal conditions, powerful winds blow steadily from east to west across the equatorial Pacific. These are the trade winds. They've been blowing in the same direction for millions of years. They do something critical. They push warm surface water westward, piling it up near Indonesia and Australia. The western Pacific sits under a thick blanket of warm water. The eastern Pacific, near South America, runs cold because deep cold water rises up from below to replace the water that got pushed away. This is normal. This is balance. Now picture someone tilting the bathtub. When the trade winds weaken, that piled up warm water in the west starts sloshing back east. Warm water spreads across the central and eastern Pacific. Cold upwelling off South America gets suppressed. Sea surface temperatures across an ocean basin the size of the continental United States plus Europe combined begin to rise. That's El Niño. And it doesn't stay in the ocean. The atmosphere above the ocean responds to surface temperature directly. Warm ocean means warm, rising air. Rising air triggers rainfall and storm systems. The entire pattern of where rain falls across the Pacific shifts. Australia and Southeast Asia go dry. Peru floods. California gets drenched. The jet stream, the high-altitude river of air that steers weather systems across North America, changes course. Everything downstream of the Pacific reorganizes. El Niño events are measured by how much surface temperatures rise in a specific region of the central Pacific, called the Niño 3.4 region. A rise of 0.5 degrees Celsius above normal for 5 consecutive months counts as an official El Niño. A rise of 1.5 degrees or more is classified as strong. A rise of 2 degrees or more is a super El Niño. The difference between a strong and a super El Niño isn't just statistical. It's the difference between a disruptive year and a catastrophic one. In confirmed strong El Niño years, coral reefs bleach at mass scale. Fisheries collapse along the coasts of South America. Droughts hit India, Southeast Asia, and Australia simultaneously. Floods devastate Ecuador and Peru. The changes aren't local, they're planetary. In super El Niño years, the effects multiply. The 1997 to 1998 super El Niño killed an estimated 23,000 people worldwide. The 2015 to 2016 event pushed global average temperatures to record highs and bleached more than half of the Great Barrier Reef. In 2026, scientists are watching all of the precursors that preceded both of those events, stacking up simultaneously. The trade winds in the Pacific have been weakening. Warm surface water has already started sliding east. The Kelvin wave, carrying 6 to 7 degrees of heat below the surface, is closing in on the eastern Pacific. The ocean is tilting. And the question scientists are now wrestling with is no longer whether El Niño is coming. The question is how strong it gets, and whether one specific category, the one only seen 4 times in recorded history, is about to make its 5th appearance. On May 14th, 2026, the National Oceanic and Atmospheric Administration published an update that climate scientists have been waiting for. The probability of El Niño developing by July 2026, 82%. 1 month earlier, that same number had been 61%. The jump of 21 percentage points in a single month was significant. It meant the evidence had accumulated faster than expected. The signs were no longer subtle. NOAA's forecast didn't stop there. The agency projected that once El Niño developed, it would almost certainly persist through the winter. The probability of continuation through the end of 2026, 96%. And the probability of the event reaching strong or very strong classification, 66%. 2 out of 3 odds of a strong El Niño. Those are not cautious numbers. For a government agency that traditionally phrases forecasts conservatively, these numbers represent a high level of certainty. To understand what changed NOAA's confidence so dramatically between April and May, you have to look at what their models were seeing. The subsurface Kelvin wave was continuing to intensify. The Niño 3.4 surface index was climbing toward the threshold that officially defines El Niño. Wind patterns across the western Pacific were shifting in the direction that historically precedes El Niño development. And crucially, the models that had proven most accurate in predicting past El Niño events were all pointing toward the same outcome. NOAA's North American Multi-Model Ensemble, which combines the forecasts of multiple climate prediction systems, was estimating by mid-May that the Niño 3.4 region was just below the plus 0.5 threshold that formally declares El Niño. Projections placed it crossing that threshold within weeks. There is a complication, however, and NOAA was transparent about it. Spring is the hardest time of year to make accurate El Niño forecasts. Scientists call it the spring predictability barrier. Climate models made in spring have a documented tendency to overestimate how strong El Niño will become. The ocean in spring is in a transitional state, and small errors in the models can compound into large errors by summer. NOAA's climate scientist Emily Becker stated plainly that there is a well-documented tendency for computer models to predict surface temperatures in the tropical Pacific that are significantly stronger than what actually occurs. This is an important check. 82% probability of El Niño developing is high confidence. The strength of that El Niño, especially whether it reaches super El Niño status, remains genuinely uncertain. What NOAA did confirm was the wildcard scenario, the probability of a super El Niño, defined as Central Pacific warming of at least 2 degrees above average, for the November through January window, 33 to 37%. That's roughly 1 in 3 odds, up from 1 in 4 just a month earlier, 1 in 3 odds of the rarest and most destructive category of El Niño in a year when the ocean is already running near record temperatures. Columbia University's International Research Institute for Climate Forecasting placed the probability of El Niño remaining dominant through the rest of 2026 at 88 to 94%. The World Meteorological Organization confirmed El Niño could begin as early as May to July 2026. The forecast community was aligned. The ocean was moving in one direction. And while scientists were analysing delta and running models, the Pacific had already sent its first unmistakable signal: a storm. Formed in April, when the Pacific almost never produces anything dangerous, it didn't stay small for long. April is supposed to be quiet in the Northwest Pacific. Typhoon season officially runs from May through November. The peak sits in late August and September. April storms happen, but they are rare and weak. The ocean hasn't warmed enough. The atmospheric conditions that allow storms to organise and strengthen rarely align that early in the year. April 2026 was different. On April 8th, a loosely organised cluster of thunderstorms appeared north of the Cook Islands in Micronesia. Chuuk is a chain of small islands in the Central Pacific, roughly halfway between the Philippines and Hawaii. The system had no name yet. Weather agencies were watching it, but it didn't look exceptional. On April 9th, the system organised enough to be named. It became Tropical Storm Sinlaku. The conditions around it were unusual for April. Sea surface temperatures in the area were running at 82 to 84 degrees Fahrenheit. That's the kind of water temperature you normally see during peak typhoon season in August, when the Pacific has had months of summer sun to build up heat. Sinlaku found those temperatures in April because the Pacific had never properly cooled down from the previous year. A tropical storm needs warm water like a fire needs fuel. The warmer the water, the more energy the storm can pull upward into its core. At 82 to 84 degrees, Sinlaku had more fuel available in April than most typhoons find during their peak season months. The storm started moving northwest, tracking toward the Northern Mariana Islands. Weather forecasters issued advisories. The forecast track was concerning but manageable. Sinlaku was a tropical storm, and tropical storms, while capable of damage, are a known and manageable hazard. Then the atmosphere above the storm changed. Wind shear is the enemy of tropical cyclones. When winds at different altitudes blow in different directions, they tear a storm apart before it can organise. In April 2026, the upper atmosphere above Sinlaku was unusually calm. The wind shear that should have been there, that would have capped the storm's growth, was absent. A pocket of a low wind shear opened up directly over the storm's path. With warm water below and calm air above, Sinlaku had everything it needed. The storm began pulling more heat from the ocean. Its rotation tightened. Its central pressure started dropping, and in the world of tropical cyclones, dropping pressure means increasing power. On April 10th, Sinlaku crossed the threshold into Category 1 typhoon status with sustained winds of 85 miles per hour. Still dangerous, still manageable. Forecasters were watching closely but hadn't yet raised the alarm beyond standard typhoon warnings. Nobody in the forecast community was fully prepared for what happened over the next 30 hours. The water ahead of Sinlaku was as warm as any ocean anywhere in the world. The storm was organised, compact, and sitting under a perfectly calm upper atmosphere. All of the ingredients for one of the most violent weather events of the year were in place. Sinlaku began to accelerate. What happened between April 11th and April 12th has now entered the record books. Forecasters would later describe it as one of the most alarming rapid intensification events in the modern history of Pacific typhoon tracking, and it happened in April, in a month when storms like this are essentially never supposed to exist. On the morning of April 11th, Sinlaku had winds of 85 miles per hour. By the morning of April 12th, it had winds of 155 miles per hour, 30 hours, Category 1 to Category 5, in April. This process has a name: rapid intensification. Meteorologists define it precisely. A storm qualifies as rapidly intensifying when its sustained winds increase by at least 35 miles per hour within a 24-hour period. Sinlaku didn't just meet that threshold, it blew past it. The storm intensified at nearly 3 times the rate required to qualify as rapid intensification, and it kept accelerating. To picture what this feels like from the inside of the storm, imagine the eye of Sinlaku as it collapsed in size. As a typhoon intensifies rapidly, its eye shrinks and its eye wall, the ring of the most violent winds surrounding the calm centre contracts inward. The wind speeds at the eye wall increase dramatically. The pressure at the centre drops. The storm becomes more organised, more efficient, and vastly more dangerous. On April 12th, Sinlaku reached its peak. Sustained winds of 185 miles per hour. Central pressure of 896 millibars. The pressure reading is critical. Pressure is how meteorologists measure a storm's true power. The lower the pressure at the centre, the more violent the storm. 896 millibars place Sinlaku among a very small number of Pacific typhoons ever recorded. Most typhoons never get below 900 millibars. The most powerful tropical cyclone ever recorded, Super Typhoon Tip in 1979, reached 870 millibars. Sinlaku in April came close. A 2026 study published in Nature confirmed that roughly 96% of all storms that have ever achieved super typhoon status did so through at least one episode of rapid intensification. The process is not random. It requires three ingredients: warm ocean water deep enough that the storm can't churn up cooler water from below, low wind shear in the upper atmosphere, and a well-organized storm structure ready to accelerate. In April 2026, the Pacific provided all three simultaneously. The ocean was the warmest it had ever been for that time of year. The atmosphere was calm at altitude, and Sinlaku was perfectly positioned. Scientists confirmed afterward that the rapid intensification was textbook in its mechanics, but extraordinary in its timing. This category of storm intensifying this fast was supposed to happen in September. The fact that it happened in April was a direct consequence of the ocean not cooling between the 2024 El Niño and the developing conditions of 2026. For people living along Pacific coastlines, the timing is what should be alarming. Peak typhoon season is still months away. The ocean will be even warmer by August. The atmospheric conditions that enabled Sinlaku's intensification will be even more favourable. Sinlaku intensified in April with near-record warmth. Storms forming in August will find ocean temperatures potentially beyond any historical comparison. Sinlaku was still intensifying when it locked onto the Northern Mariana Islands. The islands of Tinian and Saipan lay directly in its path. Combined, they are home to roughly 50,000 people, all of them American citizens, sitting on a strip of land in the middle of the Pacific Ocean with a Category 5 typhoon bearing down on them. The storm had weakened slightly by the time it arrived, but only slightly. Numbers are easy to say: 185 miles per hour, 4 syllables, a moment of reading. Standing inside that wind is something different. At 150 miles per hour, sustained winds strip bark from trees. They send ordinary objects, rocks, boards, pieces of roofing, through the air at speeds that turn them into weapons. Concrete walls crack, steel structures bend. The sound is constant, overwhelming, and described by survivors of storms this powerful as something between a freight train and a jet engine, sustained for hours without stopping. At 185 miles per hour, the sustained winds of Sinlaku at peak intensity, the air itself becomes a battering ram. The pressure difference between one side of a building and the other is strong enough to collapse walls inward. Roofs don't peel off, they explode upward. Cars become projectiles. The 896 millibar central pressure inside Sinlaku's eye tells a specific story. Pressure is measured in millibars because meteorologists need a precise number for a force that can't be seen directly. Standard sea level pressure on a calm day sits around 1013 millibars. Every millibar of pressure that drops below that number represents the storm pulling the atmosphere slightly harder. At 896 millibars, Sinlaku was pulling so hard that the sea surface directly beneath the eye physically rises, creating a dome of elevated ocean water. That dome of water is called the storm surge. When it reaches a coastline, it doesn't arrive as waves. It arrives as a wall of ocean that simply advances over land. In storms with pressures near 900 millibars, storm surge can pile 10 to 20 feet of seawater onto low-lying islands. Sinlaku was the second strongest Pacific typhoon ever to form between January and April, behind only Super Typhoon Hester in 1953. 73 years had passed between Hester and Sinlaku. The conditions that created Sinlaku, specifically that near-record April ocean warmth, had never existed at this time of year in the intervening decades, and Sinlaku was not alone. During the same week that Sinlaku was intensifying toward peak strength, 2 other tropical storms were active simultaneously in the Pacific Basin: Tropical Storm Mela and Tropical Storm Vaianu. 3 active Pacific tropical systems during April, a month when the Pacific historically averages fewer than 1. The concurrent development of 3 systems is extremely rare even during peak season. 3 storms. April. Because the ocean refused to cool, Sinlaku reached its 185 mile per hour peak on April 12th. Then it began to weaken slightly as it moved over marginally cooler water and encountered increased wind shear. But the Northern Mariana Islands were now within range, and the storm still had tremendous power. On April 14th, Sinlaku made landfall on the islands of Tinian and Saipan. It arrived as a Category 4 typhoon, with sustained winds of 150 miles per hour, slightly weaker than its peak. Still among the most powerful storms ever to strike American territory in the Pacific. 50,000 people on those islands had been watching the forecasts. They knew something enormous was coming. But forecasting landfall intensity for a rapidly evolving storm is imprecise even with modern technology. What hit the islands on the evening of April 14th was beyond what many residents had experienced in their lifetimes. Saipan and Tinian are small islands. Together they cover less than 60 square miles of land, sitting in the middle of the Pacific Ocean, roughly 1,500 miles east of the Philippines. The 50,000 American citizens who lived there had seen typhoons before. The Northern Mariana Islands sit in one of the most storm-active regions on Earth. Evacuations had been ordered. Residents who could leave had left. Those who couldn't were sheltering in place, in concrete buildings or government shelters, waiting. Sinlaku made contact on the evening of April 14th. 150 miles per hour of sustained winds arrived with no gradual build-up. The outer bands of the storm had been battering the islands for hours before the eyewall reached shore. But the eyewall itself was the point of maximum violence. It brought rain falling sideways with enough force to shred plants down to bare stems. It brought storm surge flooding low-lying coastal areas. And it brought more than 20 inches of rainfall across the islands in a matter of hours. 20 inches of rain in hours means water accumulating faster than any drainage system can handle. Roads became rivers. Ground floors of buildings flooded before the winds had even reached peak strength. The combination of wind, surge, and flooding is what makes landfalling storms so catastrophic. Each hazard amplifies the others. Power across the islands went out almost immediately. The electrical infrastructure, a network of above-ground lines across relatively flat terrain, was among the first casualties. By the time Sinlaku's eyewall cleared the islands, the power was gone. Nearly all 50,000 residents were without electricity. Structural damage was widespread. Homes built to standard Pacific construction, which means reinforced concrete by local codes, survived better than wood frame structures. Wood frame buildings, sheds, older homes, and any structure that hadn't been updated to modern standards suffered severe damage or total destruction. Roofs came off. Windows imploded. Vehicles were moved by floodwater. The Northern Mariana Islands are American territory. The federal response was coordinated through emergency management channels, and aid began arriving within days. But for the people on those islands, the days immediately after a storm that powerful, with no power, damaged roads, and flooding still receding, carry their own kind of danger. Sinlaku dissipated on April 20th after weakening over the open North Pacific. The immediate story of the storm was over, but the actual significance of Sinlaku was only beginning to be understood. A team of meteorologists and climate scientists began analysing what the storm's rapid development told them about the state of the Pacific in 2026. And what they found wasn't just about Sinlaku itself. The storm hadn't just responded to the warm ocean. According to the data, it had actively made things worse. Super Typhoon Sinlaku, by forming and intensifying so rapidly, had generated something called a westerly wind burst, a powerful pulse of wind moving in exactly the wrong direction, opposite to the trade winds, pushing warm water further east. That wind burst, generated by the storm itself, had accelerated the process that scientists were already tracking. Sinlaku hadn't just been a symptom of the developing Pacific conditions, it had helped cause the next stage. A typhoon creates itself, devastates everything in its path, and then dies over the open ocean. Most people assume the story ends there. The storm is gone, the ocean rebuilds, the atmosphere resets. In 2026, that assumption was wrong. When Super Typhoon Sinlaku formed and rapidly intensified in the Western Pacific, its massive rotating wind field did something that most storms do in a smaller way. It pushed air westward at high altitude and generated strong surface winds blowing in the opposite direction, toward the west, fighting against the normal eastward flow of air that the trade winds create. These pulses of westward flowing surface wind are called westerly wind bursts. They are a key mechanism in El Niño development. When a westerly wind burst occurs, it directly fights against the trade winds. It weakens them. And when the trade winds weaken, warm water that was being held in the Western Pacific starts sloshing east. Ocean temperatures rise across the Central Pacific. El Niño strengthens. Sinlaku generated one of the strongest westerly wind bursts recorded in the Western Pacific during the spring of 2026. Climate meteorologist Tom Skilling, commenting on April 11th while the storm was still intensifying, stated that Sinlaku's development was essentially igniting El Niño ahead of schedule, with rapid intensification likely to follow for the developing climate pattern. Here is where the feedback loop becomes alarming. Warmer ocean temperatures produce more frequent and more intense typhoons. More intense typhoons generate stronger westerly wind bursts. Stronger westerly wind bursts weaken the trade winds further. Weaker trade winds allow the ocean to warm more. More ocean warming produces more intense typhoons. The process feeds itself. This is what climate scientists mean when they discuss the interaction between tropical cyclones and El Niño. Each major typhoon is not just a weather event. It is also a participant in the climate system, actively pushing that system in a direction that will produce the next typhoon and make it stronger. The pattern in 2026 matched almost precisely what happened in the spring of 1997. In that year, a series of early Pacific typhoons generated westerly wind bursts that preceded and accelerated the strongest El Niño ever recorded. By the summer of 1997, conditions in the Pacific were unlike anything seen in the modern measurement era. That El Niño went on to produce the 1997 to 1998 season that devastated communities across South America, triggered catastrophic droughts in Southeast Asia and Australia, and ultimately killed tens of thousands of people worldwide. Dynamic climate models throughout April and May 2026 were consistently projecting record strength or near record strength El Niño conditions for the second half of 2026. But understanding exactly how that escalation works requires understanding the single mechanism at the center of everything: the trade winds, why they exist, why they have been weakening, and what the Pacific looks like when they finally break down completely. That process is happening right now, and the details of it reveal something that most people living near a Pacific coastline have never been told. For millions of years, the equatorial Pacific has operated on a simple system. Winds blow west, warm water piles up in the west, cold water rises in the east. Everything stays in balance. The trade winds are what make that system work. They blow steadily from the coast of South America westward toward Asia, driven by the temperature difference between the warm tropics and the cooler regions north and south. They are among the most consistent wind patterns on Earth. Sailors in the age of wooden ships relied on them to cross the Pacific. They don't vary much, they're just there. When they weaken, the entire Pacific reorganizes. In 2026, the trade winds have been losing strength for months. The specific atmospheric conditions that maintain trade wind intensity depend on a pressure difference between the eastern and western Pacific. When that pressure difference shrinks, the winds slow down, and in 2026 that pressure difference has been shrinking at a rate that alarms atmospheric scientists. Part of the reason is the ocean itself. Warmer water in the central and eastern Pacific reduces the temperature contrast that drives the trade winds. When the eastern Pacific warms up, the winds driving that warm water westward slow down. Less pushing means warm water spreads east. More warm water in the east means even less temperature contrast. The winds slow further. This is called the Bjerknes feedback. It operates as a one-way escalator once it starts moving in a strong enough direction. In April 2026, atmospheric pressure readings in the Western Pacific were already showing the signature of weakening trade winds. The data matched what climate models had been projecting for months. Super Typhoon Sinlaku's westerly wind burst had accelerated the process, pushing additional warm water eastward across the central Pacific. By mid-May, the Niño 3.4 index was approaching the threshold for El Niño declaration. The trade winds weren't gone, they were still there, still blowing westward. But they had lost enough strength that the Pacific was already responding as if El Niño had begun. Warm water was spreading east. Sea surface temperatures in the central Pacific were rising. The cold upwelling that normally keeps the eastern Pacific cool was beginning to weaken. The system was tilting. For the average person, the trade wind collapse is the invisible event behind every storm season headline in 2026. It doesn't make news directly. Nobody films the trade winds weakening. There's no dramatic footage to broadcast, but it is the underlying cause of nearly every extreme weather outcome currently forecast for the second half of the year. In a year when the trade winds fail completely, The Pacific delivers its most destructive storms. It sends rain where there should be drought and drought where there should be rain. It reorganizes the jet stream over North America, shifting storm tracks in ways that affect the entire continental United States. It pushes ocean temperatures in the central Pacific to levels that fuel typhoons at any time of year. Right now, in May 2026, the trade winds are weakening. The tilt is underway, and there is a specific classification for what happens if this process doesn't just produce a regular El Niño, but goes further, much further. It has happened only 4 times since scientists started keeping records. The name for it is Super El Niño. El Niño arrives in different sizes. That sounds simple. It isn't. The difference between a moderate El Niño and a Super El Niño isn't like the difference between a rainstorm and a heavy rainstorm. It's the difference between a flooded basement and a flooded city. The same basic mechanism produces consequences that are orders of magnitude more severe. Scientists measure El Niño strength by how much ocean temperatures in the central Pacific rise above average in a specific region. The threshold to declare El Niño is plus 0.5 degrees Celsius above normal, held for 5 consecutive months. A strong El Niño reaches plus 1.5 degrees or higher. A super El Niño pushes past 2 degrees above normal. 2 degrees, it sounds like almost nothing. Imagine heating a section of ocean larger than the continental United States by 2 degrees above its already elevated baseline. Then hold it there through an entire storm season. That's the thermal energy being added to the atmosphere above it. That's the fuel being loaded into every storm system that passes over it. That's the heat being pumped into a global atmosphere that was already running at record temperatures. In a regular strong El Niño year, Pacific typhoon seasons become more active. Droughts hit Australia and Southeast Asia. Flooding strikes Peru and Ecuador. The global average temperature rises for a year or two before returning toward baseline. In a super El Niño year, all of those effects are amplified. The Australian drought becomes catastrophic and multi-year. The Peruvian flooding kills thousands. Pacific storm seasons break historical records for intensity and total energy. Global average temperature spikes far above the previous record, and because the ocean stays warm longer, the effects persist for years after the event itself ends. The 1997 to 1998 Super El Niño caused approximately $33 billion in damage adjusted for today's prices and killed an estimated 23,000 people. It destroyed fisheries along the South American coast, triggering economic collapses in fishing communities from Ecuador to Chile. It bleached coral reefs across the Pacific and Indian Oceans. It reorganized rainfall patterns across Africa, triggering both flooding and drought simultaneously in different regions of the same continent. The 2015 to 2016 Super El Niño pushed global average temperatures to a level that had never been recorded. It bleached more than half of Australia's Great Barrier Reef. It drove wildfire seasons in Indonesia that sent smoke across an area larger than Europe. Both of those events occurred in a Pacific Ocean that was cooler than the Pacific in 2026. A Super El Niño in 2026, layered on top of near-record baseline ocean temperatures, would be operating in conditions that have no historical comparison. Scientists cannot point to a previous event and say, "This is what it looked like." There is no previous event with this starting temperature. As of May 2026, the probability of a Super El Niño is approximately 1 in 3. Those are not small odds for an event of this magnitude. The 4 times it has happened before, each one left a mark that lasted years. The next chapter tells you when those 4 events occurred, what they had in common, and why the current trajectory in the Pacific resembles the start of every single one of them. Since scientists began systematically tracking Pacific Ocean temperatures in the mid-20th century, Super El Niño has happened 4 times: 1972 to 1973, 1982 to 1983, 1997 to 1998, 2015 to 2016. 4 events across roughly 75 years of careful measurement. Each one left damage that took years or decades to fully assess, and each one, when viewed in hindsight, sent clear warning signals months before it became obvious that something historic was developing. The 1972 event caught the scientific community almost entirely off guard. Monitoring systems were primitive by modern standards. The full scope of the event only became clear after the fact when researchers traced the collapse of the Peruvian anchovy fishery, one of the world's largest at the time, back to the dramatic warming of coastal waters that year. The 1982 to 1983 event was stronger and more destructive. It produced catastrophic flooding in Ecuador and Peru, severe drought across Australia and southern Africa, and mass coral bleaching across the Pacific. Scientists watching in real time initially misread the signals. The monitoring network that now covers the Pacific in sensors wasn't yet in place. The event surprised forecasters. The 1997 to 1998 event was the strongest ever recorded at the time, and for the first time, scientists were watching it build in real time with a full network of sensors. A team of researchers tracked the Kelvin wave that preceded that event, following its heat signature as it crossed the Pacific and surfaced in the Eastern Ocean. The pattern looked almost exactly like what climate analysts are describing in April and May 2026. Scott Yuknis, the climate analyst who compared 2026's subsurface heat patterns to previous super El Niño years, specifically identified 1997 as the closest match to the current trajectory. The upper ocean heat anomalies in the first months of 2026, combined with the April Kelvin wave readings, most closely resembled the acceleration seen at the start of that record-breaking event. The 2015 to 2016 event added something new, an already elevated baseline. Global temperatures had risen significantly above their 20th century average by 2015. The Super El Niño of that year operated in a warmer world than any of its predecessors and produced outcomes, including global temperature records, coral bleaching records, and wildfire records that reflected that warmer starting point. 2026 starts warmer still. The ocean baseline in 2026 is higher than it was at the start of the 2015 event. The Pacific has already set near-record April temperatures without El Niño fully engaged. A subsurface, Kelvin wave described as possibly the strongest ever recorded is approaching the surface. And the probability forecasts from NOAA, Tropical Storm Risk, and the European Centre are all pointing toward a strong to Super El Niño. If 2026 produces a fifth Super El Niño, it will do so in an ocean that no previous Super El Niño has ever encountered. The four previous events provide a framework for understanding what might happen, but the scale of the consequences could go beyond any of them. The uncertainty about exactly how strong this event becomes is real, and it matters. The scientific community is transparent about it. Spring forecasts carry specific limitations that even the best models struggle to overcome. Understanding that limitation doesn't reduce the alarm. It clarifies exactly where the uncertainty lives and what the next few months will reveal. NOAA's forecast showing 82% probability of El Niño is significant. 66% probability of strong or very strong is alarming. 33% probability of Super El Niño is a number that should make every Pacific coastline government take notice. And yet NOAA itself included a warning alongside all of those numbers. Spring is the worst time of the year to predict El Niño strength. This isn't a minor technical footnote. It's a fundamental limitation of how climate forecasting works, and it affects every confident-sounding number coming out of forecast agencies right now. The problem is called the spring predictability barrier. It exists because of the way the tropical Pacific behaves during the transition from winter to spring. In those months, the ocean and atmosphere are in a period of rapid change. Small differences in the initial conditions fed into a climate model can lead to dramatically different outcomes by summer. Models that start with slightly different ocean temperature readings in February can produce wildly different El Niño forecasts by August. Emily Becker, a climate scientist at NOAA's El Niño forecast team, described the problem directly. She stated that there is a well-documented tendency for computer models to predict Pacific surface temperatures that are significantly stronger than what actually occurs. The models often see the early signals of warming, the Kelvin wave, the weakening trade winds, the rising Niño index, and extrapolate aggressively toward a strong outcome. Sometimes that extrapolation is correct. Sometimes the event peaks lower than forecast. This has happened before. In 2014, a powerful Kelvin wave crossed the Pacific, and models predicted a Super El Niño comparable to 1997. The scientific community issued warnings. Governments prepared. The event that actually developed was moderate. The 2014 El Niño was real but far weaker than forecast. Australia's Bureau of Meteorology in May 2026 was still placing the probability of El Niño at roughly 50%. lower than NOAA's 82%. The Bureau acknowledged the warming signals, but was applying more conservative thresholds before declaring high confidence. A neutral outcome, meaning no El Niño developing at all, remained within reach according to their models, though increasingly unlikely. The honest picture then is this: the precursor signals in 2026 are stronger than they were in 2014. The Kelvin wave is larger, the surface warming is faster, the model consensus is more aligned. NOAA's 82% represents a meaningful difference from the ambiguous setup that preceded the 2014 miss. But the spring barrier is real. The certainty that forecasters have about El Niño developing doesn't extend with equal confidence to how strong it gets. Whether 2026 becomes a strong El Niño, a very strong El Niño, or a super El Niño won't be clear until at least late summer or early autumn, when the ocean and atmosphere will have moved past the period of maximum forecast uncertainty. What's certain is that the ocean is warming, the trade winds are weakening, the Kelvin wave has been delivering its heat, and the background conditions in the Pacific have never been this elevated at the start of an El Niño development cycle. One of the reference points forecasters keep returning to is a specific year, a year when the signals were this strong, the models were this aligned, and the outcome confirmed every worst-case projection. That year was 1997, and what followed it revealed what a true super El Niño does to the planet. In the spring of 1997, the Pacific looked familiar to what scientists are watching today. A large Kelvin wave had crossed the equatorial Pacific. Sea surface temperatures in the central Pacific were climbing toward record levels. Trade winds across the equatorial basin had weakened significantly. And forecasters, using the still developing monitoring systems of the mid-1990s, were beginning to warn that something historic might be building. By summer 1997, all doubt had evaporated. The Niño 3.4 index climbed past +2 degrees above normal, officially declaring it a super El Niño. By autumn, it had pushed past +2.5 degrees. At its peak in November and December of 1997, it reached levels that had never been recorded. The West Pacific typhoon season of 1997 produced an accumulated cyclone energy index of 571. Accumulated cyclone energy is a number that combines the strength and duration of all tropical storms in a season into a single figure. The higher the number, the more total destructive energy the season produced. 571 is an extraordinary figure. Climate Impact Company is now speculating that 2026 could challenge that number if the El Niño develops at full strength. The physical consequences of the 1997 to 1998 event spread across the entire planet. In Peru and Ecuador, flooding killed over 2,000 people and caused damage equivalent to roughly $8 billion in today's value. Rain fell at rates that hadn't been recorded in the historical record. Rivers rose beyond any previous flood level. Entire towns were cut off for months. In Australia, the drought was severe enough to trigger water restrictions across most of the continent. Agricultural losses ran into billions of dollars. The drought persisted through 1998 and contributed to some of the worst bushfire seasons Australia had seen in decades. In Indonesia and Malaysia, the combination of drought and El Niño-driven atmospheric changes triggered unprecedented forest fires. The smoke from those fires blanketed an area larger than the continental United States for months. Air quality reached levels dangerous to human health across multiple countries simultaneously. The economic damage ran into tens of billions of dollars. In East Africa, flooding killed thousands and displaced millions. In northeast Brazil, drought triggered crop failures that sent rural populations into cities. In the Philippines, which sits directly in the path of Pacific typhoons, the storm season brought a series of devastating landfalls. Globally, the event pushed the world's average temperature to a record high at that time. It bleached coral reefs across the Pacific, Indian and Atlantic Oceans simultaneously, the first documented global bleaching event of that scale, and it was operating in a cooler Pacific than 2026. The ocean baseline before the 1997 event was significantly lower than the ocean baseline before 2026's developing El Niño. Scientists at multiple institutions have confirmed that a comparable super El Niño in 2026, layered on top of an already near-record thermal baseline, would be working with more energy than the 1997 event from the very first day of its peak. The structural foundation beneath all of those storm seasons is something that most people have never thought about. The heat engine that drives Pacific weather isn't just the current El Niño. It's a permanent feature of the ocean that has been growing for more than a century, and it has nearly doubled in size. There is a region of the Pacific and Indian Oceans where the water never truly cools. It sits in the western Pacific and eastern Indian Ocean, stretching from the seas around Indonesia northward toward the Philippines and eastward into the central Pacific. Year-round, this region maintains surface temperatures above 28 degrees Celsius, which is about 82 degrees Fahrenheit. Scientists call it the Indo-Pacific Warm Pool. It is the single largest reservoir of the warm ocean water on Earth. It is also the heat engine that drives global atmospheric circulation. The warm, moist air rising off this pool doesn't just fuel local storms. It drives the global conveyor belt of weather. The warm pool's heat powers the monsoon systems that bring rain to India, Southeast Asia, and East Africa. It energizes the rainfall that falls on the Amazon basin. Changes in its size and temperature ripple through the global climate system in ways that affect weather far beyond the Pacific. Between 1900 and 1980, the warm pool covered approximately 22 million square kilometers. That's roughly 8.5 million square miles, an area significantly larger than the entire North American continent. By 2018, it had grown to 40 million square kilometers, nearly double its size. To picture the scale of that growth, imagine that every year since 1981, an area of new warm ocean the size of the state of California has been added to the warm pool. That's the rate of expansion, roughly 400,000 square kilometers, or about 154,000 square miles per year, added continuously every year for over 40 years. The warm pool has been expanding because the ocean has been heating unevenly. The regions of the Western Pacific that sit above the warm pool have warmed faster than the surrounding ocean, extending its boundaries northward, eastward, and southward. More ocean above 28 degrees means more ocean capable of fueling powerful storms. The consequences extend beyond storm season. A larger warm pool alters something called the Madden-Julian oscillation, which is the dominant pattern of tropical weather variability on timescales of 30 to 60 days. The Madden-Julian oscillation generates pulses of enhanced rainfall and wind that circle the tropics every month or two. When the warm pool expands, it shifts the active phase of this oscillation westward over the Pacific, increasing the frequency and intensity of strong weather systems in that region by up to 5 or 6 additional days per cycle. More days of active storm development, triggered by a warm pool that has doubled, building toward a peak season in a year when El Niño is adding further energy on top of that already elevated baseline. The warm pool isn't just a feature of the 2026 season. It's the reason 2026 is starting from a higher energy state than any previous El Niño year in recorded history. And a larger warm pool doesn't just mean more storms in general. It changes where storms form, how quickly they intensify, and which coastlines they threaten. Understanding exactly how that works reveals something about the 2026 season that the raw typhoon count forecasts don't fully capture. A larger warm pool doesn't just produce more storms, it produces different storms in different places, behaving in ways that forecasters struggle to predict using tools calibrated for a smaller version of the ocean. The traditional model of Pacific typhoon formation is relatively straightforward. Storms develop in the Western Pacific in a region roughly between 10 and 20 degrees north of the equator. They draw energy from the warm pool and intensify as they move westward or northwestward. When they exit the warm pool's warmest water, they begin to weaken. The boundaries of the warm pool effectively set the limits of where typhoons can sustain maximum intensity. When the warm pool expands, those boundaries move. Storms can now achieve and sustain peak intensity over a larger portion of the Pacific. They can maintain their destructive power for longer, before crossing into cooler water, and critically, they can intensify rapidly in regions where rapid intensification was previously uncommon, because the deep, warm water beneath an expanded warm pool suppresses the cooling effect that normally occurs when a storm churns the ocean beneath it. The churning effect is crucial. When a powerful storm moves across the ocean, its rotating winds pull cold water up from below the surface, mixing it into the warm surface layer and robbing the storm of some of its fuel. This natural break helps limit how strong a storm can get and how quickly it intensifies. In deep warm water, the cold water is too far below the surface to be churned up effectively. The brake doesn't engage, the storm keeps accelerating. An expanded warm pool means that deep churnable warm water extends over a larger area. More of the Pacific now provides the conditions for unchecked rapid intensification. Sinlaku's explosive growth in April 2026 was a direct demonstration of this. The storm found warm water deep enough to sustain rapid intensification in a region, and at a time of year when conditions like that were historically rare. The warm pool had expanded enough to put those conditions within reach in April. The implications for the rest of the 2026 season are significant. Peak typhoon season runs from late August through October. By that time, the warm pool will have absorbed additional months of solar heating and El Niño-driven warmth. The area of ocean capable of supporting rapid intensification will be at its annual maximum, and that maximum will be larger than at any comparable point in the historical record. Tropical Storm Risk's forecast of 18 typhoons in the Northwest Pacific in 2026 represents 25% above the historical average. Of those 18, 11 are expected to be intense, equivalent to Category 3 or higher. The 10-year average for intense typhoons is 8.4. 11 versus 8.4 sounds like a modest increase. Spread across storm season, those 3 extra intense typhoons represent 3 additional opportunities for the kind of rapid intensification event that Sinlaku demonstrated in April. 3 extra Category 3 or higher storms, each capable of causing the same scale of destruction that struck the northern Mariana Islands on April 14th. And the region sitting directly in the projected path of the most active part of the season is one of the most storm-exposed places on Earth. A country that sits along the western edge of the Pacific, facing the full force of whatever the typhoon season delivers. The numbers coming out of that country's own weather agency should stop anyone in their tracks. On May 12, 2026, a commercial forecasting company called Tropical Storm Risk published its first outlook for the Northwest Pacific typhoon season. The headline number: 18 typhoons. The historical average for any given year in the Northwest Pacific is roughly 14.2 typhoons. 18 represents a 25% increase above that average. But the raw typhoon count only tells part of the story. The more alarming figure is the breakdown by intensity. Of those 18 projected typhoons, 11 are expected to reach what meteorologists classify as intense, equivalent to Category 3 or stronger on the scale used for Atlantic hurricanes. The 10-year average for intense typhoons in the Northwest Pacific is 8.4. 11 intense typhoons versus an average of 8.4 means roughly 3 additional catastrophic level storms above what any given season normally produces. 3 extra Category 3 or higher typhoons, each one capable of winds exceeding 111 miles per hour at minimum and potentially far stronger. Each one capable of devastating landfall on any coastline in its path. Tropical Storm Risk's forecast placed 2026 on track to be the most active Northwest Pacific typhoon season since 2015. That year, 2015, was the year of the last Super El Niño. The parallels between that season and 2026's setup are ones forecasters have been noting explicitly for months. The European Centre for Medium-Range Weather Forecasts independently released projections showing above normal tropical storm numbers in the Northwest Pacific for the summer months. 2 major forecasting institutions, using different models and different methodologies, arriving at the same general conclusion. 2026 will produce more storms, and more intense storms, than a typical year. Climate Impact Company went further. Their analysts suggested that 2026 could become the most active tropical cyclone season on record for the entire North Pacific, combining both the Northwest and Eastern Pacific basins. The benchmark for comparison is 1997, the year of the last Super El Niño comparable, in setup to what 2026 is currently tracking toward. That year, the West Pacific alone accumulated 571 accumulated cyclone energy units. The measure captures both the number and the intensity of storms, combined into a single figure that reflects total destructive output across a season. Sinlaku alone, a single storm in April, accumulated an accumulated cyclone energy value of 40.6, an extraordinary number for one April storm. Peak season, from late August through October, is still months away. The real-world translation of these forecast numbers isn't abstract. More intense typhoons in the northwest Pacific means more landfalls on the coasts of the Philippines, Japan, Taiwan, Guam, and Vietnam. It means more storm surge events, more flooding, more infrastructure damage, more agricultural losses, more displacement of coastal populations, and the country sitting at the geographic centre of the northwest Pacific storm track, absorbing more landfalling typhoons than any other nation on Earth, is already receiving forecasts from its own weather agency that go beyond anything tropical storm risk projected. The Philippine Atmospheric, Geophysical and Astronomical Services Administration projected 9 to 17 tropical cyclones entering its area of responsibility between May and October 2026. 17 is at the extreme upper end of any historical season. The agency's chief made a statement that framed the danger more precisely than any number could. The Philippines sits in the path of more typhoons per year than almost any other country on Earth, positioned at the western edge of the Pacific, directly in the lane where northwest Pacific typhoons travel, as they intensify over warm water and move toward coastlines. The archipelago of over 7,000 islands absorbs an average of roughly 20 tropical cyclones per year entering its area of responsibility, with 8 to 9 typically making direct landfall. In 2026, the Philippine Atmospheric, Geophysical and Astronomical Services Administration projected 9 to 17 tropical cyclones entering Philippine waters between May and October alone. 9 to 17. The range is wide because forecasting the exact number this far in advance is genuinely uncertain. The lower end of that range represents a roughly average season. The upper end represents one of the most active 6-month periods in Philippine weather history. Pagasa's chief, Nathaniel Servando, added context that reframed the entire forecast. He stated that while the total number of storms entering Philippine waters might not set an all-time record, the storms that do form are expected to reach typhoon or super typhoon intensity at significantly higher rates than normal. Fewer weak storms, more catastrophic ones. He described it as a situation where the quality of the threat was increasing even if the quantity remained within a historical range. This is the worst-case framing for emergency preparedness. A season with many weak storms gives communities time to recover between events. A season with fewer but more intense storms concentrates the damage. Recovery infrastructure, evacuation systems, and emergency supplies designed around historical averages get overwhelmed when the events arriving are stronger than anything the planning was built around. The Philippines has experienced what super-strength Pacific storms do at landfall. Super Typhoon Haiyan struck the Philippines in November of 2013 with sustained winds of 195 miles per hour, making it one of the most powerful tropical cyclones ever recorded at landfall. More than 6,000 people died. Entire cities were flattened. The storm surge reached heights of 20 feet in some coastal areas. Haiyan formed and intensified in a Pacific Ocean cooler than the Pacific in 2026. Research from the University of the Philippines warns that future Philippine typhoons will carry higher damage potential as both atmospheric and ocean temperatures continue rising. The study projected increasing frequency of rapid intensification events in the region, meaning storms that arrive with far more intensity than early track forecasts suggest. Communities that evacuate based on a Category 2 forecast and receive a Category 4 landfall face catastrophic consequences. The geography of the Philippines amplifies every typhoon risk. Thousands of islands mean thousands of coastlines. Millions of people live in low-lying coastal areas with limited evacuation infrastructure. Mountain terrain channels storm surge flooding into valleys. Agricultural land concentrated in storm tracks means food production losses that persist for years after a single event. Pagasa's forecast for 2026 represents a scientifically grounded warning that a country already accustomed to typhoon damage should prepare for something beyond the normal range. And the Philippines isn't the only nation in 2026 facing an extraordinary threat. The same system that's fueling record Pacific typhoon activity is doing something strange and alarming to storms on the other side of the ocean basin, something that most people haven't connected to El Niño at all. In April 2026, Sinlaku went from Category 1 to Category 5 in 30 hours. That kind of escalation used to be exceptional, something that happened once in a decade, maybe less. A meteorological outlier that forecasters noted and studied and filed away as a rare event. A study published in Nature in January 2026 revealed that this is no longer exceptional. Researchers analysed data on tropical cyclones between 1990 and 2021. They found that roughly 40% of all tropical cyclones during that period experienced at least one episode of rapid intensification during their lifetime, and among storms that achieved super typhoon status specifically, 96% got there through rapid intensification. 40%. Nearly 1 in 2 storms is now going through explosive strengthening at some point. The definition of rapid intensification requires a storm's sustained winds to increase by at least 35 miles per hour within 24 hours. Sinlaku increased by 70 miles per hour in 30 hours, double the threshold in a slightly longer window. The study's data shows that the most extreme intensification events, the ones like Sinlaku, are becoming more common alongside the broader trend. The driver is straightforward. Warmer ocean water holds more thermal energy. More thermal energy available to a developing storm means more fuel for intensification. The rate at which a storm can pull heat upward from the ocean and convert it into wind energy increases when the water is warmer. And in 2026, the water is warmer than it has ever been at this time of year. There is a second mechanism that amplifies the problem. Rapid intensification works most efficiently when the storm can't cool the water beneath it by churning up colder water from depth. A storm spinning over warm surface water will pull cold water up from below if the cold water sits close enough to the surface. In a normal Pacific, that cold water layer sits at a moderate depth, close enough to be accessed by a powerful storm's churning winds. In an expanded warm pool, the warm water extends much deeper. The cold layer is too far down to be reached. The storm spins over water that stays warm no matter how hard it churns. The cooling break never engages. Rapid intensification proceeds unchecked. For coastal populations, the practical consequence is a forecasting problem. Agencies issue warnings based on projected storm intensity at landfall. Those projections use historical models of how quickly storms intensify. But if 40% of storms are now experiencing rapid intensification, and the most extreme episodes are becoming more common, the gap between the forecast intensity and the actual landfall intensity is growing. A community told to prepare for Category 2 winds and receiving Category 4 winds doesn't have the time to respond to the difference. Evacuation decisions are made hours before landfall. Building shelter choices are made the night before. When a storm intensifies rapidly in the final hours before landfall, those decisions are already locked in. Sinlaku intensified at extraordinary speed in April, months before peak season. August storms will find ocean conditions even more favourable for rapid intensification than the water Sinlaku used. The mechanism behind this isn't limited to the Northwest Pacific. The same warm ocean, the same deep heat, the same absence of the cooling break is operating across an entirely different storm basin, one that sits on the other side of the Pacific, directly threatening coastlines that most people don't associate with catastrophic storm seasons. A typhoon forecast from 48 hours out used to carry meaningful accuracy. Meteorologists could look at a storm's current intensity, track where it was heading, model the ocean temperatures and atmospheric conditions along its path, and produce a forecast that gave coastal communities enough time to evacuate and prepare. The system worked reasonably well for most storms across most of typhoon history. Rapid intensification broke that system. When a storm strengthens explosively in its final hours before landfall, the 48-hour forecast becomes unreliable. A Category 2 storm becomes a Category 4 before anyone has time to update the evacuation orders. The entire emergency response framework, built around forecast lead times, collapses. In 2026, there are specific reasons why this problem is worse than in any previous season. The first is the geographic expansion of the rapid intensification zone. Historically, the region of the Northwest Pacific where storms could undergo explosive strengthening was concentrated in a relatively defined area around the warmest parts of the warm pool. Outside that core zone, cooler water or increased wind shear would typically cap intensification rates. As the warm pool has expanded, that core zone has grown. Storms that would previously have been entering cooler water and beginning to weaken can now continue intensifying in ocean regions that were previously too cool to support it. The second is timing. Peak rapid intensification risk used to be concentrated in August and September, when ocean heat content reached its annual maximum. Sinlaku demonstrated that April ocean conditions in 2026 were already warm enough to support explosive intensification. This extends the window of rapid intensification risk across more months of the year. Storms forming in May, June and July, traditionally a period when intensification was more gradual, now face ocean conditions previously associated with late-season peak activity. The third factor is the depth of warm water. Modern forecast models use ocean heat content, not just surface temperature, to estimate intensification potential. The subsurface Kelvin wave that crossed the Pacific in early 2026 loaded enormous thermal energy into the water column below the surface. Even storms that temporarily cool their immediate vicinity through churning can find fresh warm water below. The energy reservoir doesn't deplete the way it would in a historically normal ocean. Research from the University of the Philippines, published ahead of the 2026 season, warned specifically that intensification rates for Philippine region typhoons are trending higher. Storms that previously plateaued at Category 3 are reaching Category 4. Storms that previously peaked at Category 4 are reaching Category 5. The distribution is shifting toward higher maximum intensities. For governments managing emergency response across Pacific coastlines, the challenge is institutional. Evacuation orders require political will, public compliance, and logistical capacity. Each of those factors erodes when populations experience false alarms or over-forecasted events. If agencies issue maximum warnings for every approaching storm to account for rapid intensification risk, public trust in warnings diminishes over time. The 2026 season will test that institutional challenge more severely than any season in recent memory, and the storm risk in 2026 isn't contained to the Northwest Pacific. On May 15th, a second storm basin opened its official season, one that rarely receives the same attention, but is tracking toward its own record-breaking year. May 15th, 2026. Today. The Eastern Pacific hurricane season officially opened. The Eastern Pacific Basin stretches from the coast of Mexico and Central America westward, across the tropical ocean toward Hawaii. It is separate from the Northwest Pacific Typhoon Basin and separate from the Atlantic Hurricane Basin. It runs its own season, produces its own storms, and affects its own coastlines. In most years, it receives far less public attention than the Atlantic. Atlantic storms threaten the Gulf Coast, the eastern seaboard, and the Caribbean. Those are heavily populated, heavily reported regions. Eastern Pacific storms typically curve away from land, spending most of their lives over open ocean before dissipating harmlessly. In El Niño years, that pattern changes. AccuWeather's forecast for the 2026 Eastern Pacific season projects 17 to 22 named storms, 9 to 13 hurricanes, and 4 to 8 major hurricanes. The long-term averages for the Eastern Pacific are 15 tropical cyclones, 8 hurricanes, and 4 intense hurricanes. Even the lower end of AccuWeather's range sits above average. The upper end represents an extraordinary season by any historical standard. The reason is the same as in the Northwest Pacific: water temperature. The Eastern Pacific in 2026 is running significantly above normal. A massive marine heat wave has been holding coastal water temperatures 3 to 4 degrees Fahrenheit above normal along the west coast of the United States since mid-2025. In the tropical Eastern Pacific, where hurricanes actually form, sea surface temperatures are primed for an active season. The Central Pacific, the stretch of ocean around Hawaii, is forecast separately. Projections call for 3 to 7 named storms in that region, with 2 to 4 hurricanes and 1 to 3 major hurricanes. Hawaii sits squarely within range of Central Pacific systems in years when El Niño shifts storm tracks northward. Climate Impact Company flagged the Southeast Pacific marine heat wave specifically, describing its strength as record level, and warned that storms forming in the Eastern Pacific Basin in 2026 face conditions capable of supporting intensity levels well above historical norms for the region. As of May 15th, no active systems were present in the eastern Pacific. The season was calm at opening, as it typically is. The threat isn't in what exists today. The threat is in what the ocean will deliver over the next 6 months as El Niño continues to build and the water accumulates additional heat through summer. For residents of coastal Mexico, Central America, and the American Southwest, the Eastern Pacific season deserves attention that it rarely receives in non-El Niño years. And El Niño does something specific to Eastern Pacific storm tracks that represents one of the most consequential and least understood risks of the 2026 season. It redirects storms toward coastlines they normally miss, toward places that have never built the evacuation infrastructure, the storm-hardened buildings, or the emergency response systems that Atlantic coast communities have spent decades developing. The destination those storms are being pointed toward is somewhere most people would never expect. In a normal year, Eastern Pacific hurricanes curve harmlessly west. They form off the coast of Mexico, spiral counterclockwise, and then get steered by upper-level winds away from land, out over open ocean. They spend their lives at sea, weaken and dissipate without affecting populated coastlines. California, despite sitting at the edge of the Eastern Pacific Basin, almost never sees significant tropical storm impacts. El Niño changes the steering. Under El Niño conditions, the subtropical jet stream over North America shifts southward and intensifies. This changes the direction that upper-level winds push tropical storm systems. Instead of recurving west and away from land, storms in strong El Niño years have a documented tendency to track north, toward Baja California, toward the Mexican Pacific coast, and in the strongest events towards Southern California and the American Southwest. This is confirmed history. During the 2015 to 2016 Super El Niño, the Eastern Pacific produced a record-breaking hurricane season. Multiple storms tracked farther north than typical before weakening. The remnants of those systems brought flooding rain to regions of the American Southwest that receive almost no summer precipitation in normal years. Climate Impact Company, in its analysis of 2026, specifically warned that Mexico, the American Southwest, and possibly Southern California should prepare for major flooding rainfall events during peak tropical storm season. For Southern California, the threat isn't necessarily a direct hurricane landfall, which remains unlikely even in El Niño years. The threat is rainfall. A weakening tropical system, even one that falls apart before making landfall, can pull its moisture train inland and dump enormous amounts of rain over terrain not built for it. Southern California's drainage infrastructure is designed around its desert climate. In a normal year, it handles the rain it receives. In an El Niño year with active tropical systems tracking north, a single storm remnant can overwhelm that infrastructure. Flash flooding in canyons and hillsides, landslides on slopes already destabilized by previous fire seasons, flooding on freeways and in neighborhoods built in what were dry riverbeds for most of the century. California isn't alone in this exposure. Arizona, Nevada, and New Mexico all sit in regions that receive dramatically increased summer and fall precipitation during strong El Niño events, driven partly by the northward shifted storm tracks of Eastern Pacific systems. The 2015 to 2016 comparison is instructive, that Super El Niño produced a central North Pacific hurricane season that broke all historical records, with an unprecedented number of storms affecting Hawaii and the surrounding ocean. Hawaii experienced direct impacts from tropical systems that would never have reached those latitudes in a neutral or La Niña year. If 2026 produces a comparable or stronger Super El Niño, the Central Pacific and the American West face a season unlike anything most of their residents have ever prepared for. Meanwhile, the ocean on the other side of the continent is behaving in a way that seems to contradict everything happening in the Pacific. The Atlantic is running in the opposite direction, and the reason why reveals something fundamental about how El Niño reshapes the entire planet's storm systems simultaneously. While the Pacific builds toward one of its most dangerous seasons in history, the Atlantic is heading in the opposite direction. Colorado State University released its 2026 Atlantic hurricane season forecast on April 9th. The projection: 13 named storms, 6 hurricanes, and 3 major hurricanes. The historical averages for the Atlantic are 14 named storms, 7 hurricanes, and 3 major hurricanes. Colorado State's forecast sits below average across every metric. For a region that experienced several devastating above-average Atlantic seasons in recent years, a below-average forecast sounds like good news. The reason behind it, however, is a reminder that no part of the global weather system is insulated from what's happening in the Pacific. El Niño suppresses Atlantic hurricane activity through a mechanism called vertical wind shear. Wind shear is the difference in wind speed or direction between different altitudes in the atmosphere. At the surface, a hurricane spins with its organized circular structure. At higher altitudes, the same circulation needs the winds around it to remain relatively consistent. When winds at altitude blow strongly in a different direction from the surface circulation, they tilt the storm's structure and tear it apart. The storm can't organize or maintain intensity. El Niño strengthens the upper-level jet stream over the tropical Atlantic. That stronger jet stream generates wind shear across exactly the zone where Atlantic hurricanes form and intensify. Developing storm systems get disrupted before they can organize into threats. Existing storms get sheared apart before they can reach major hurricane status. This relationship between El Niño and reduced Atlantic activity is one of the most documented patterns in tropical meteorology. It has held consistently across multiple El Niño events. When the Pacific is in a strong El Niño, the Atlantic almost always sees reduced hurricane activity. The irony of 2026 is stark. The same climate system delivering a potentially historic Pacific typhoon season is simultaneously protecting the Atlantic coast. Communities in Florida, the Gulf Coast, and the Caribbean that have spent years preparing for devastating Atlantic hurricane seasons may experience relative relief in 2026, while communities in the Philippines, Japan, Taiwan, and the American West face extraordinary risk. But the quieter Atlantic doesn't mean the Atlantic is risk-free. 13 named storms still represent a meaningful threat, particularly given that even a single catastrophic landfall can define an entire season. And El Niño's suppressive effect on Atlantic activity is statistical, not absolute. A below-average season can still produce an Andrew, a Katrina, or a Maria. The broader point is that El Niño doesn't reduce global storm energy. It redistributes it. Less into the Atlantic, vastly more into the Pacific. The total atmospheric energy in the system remains enormous. The Pacific simply becomes its primary outlet. And within the Pacific, the mechanism that will determine exactly how much energy gets released is still moving toward its final position. The Kelvin wave that crossed the Pacific, carrying temperatures 6 to 7 degrees above normal, is approaching the eastern edge of the ocean. What happens when it surfaces off the coast of South America is the event that will confirm or deny whether 2026 becomes a year that surpasses every previous record. The Kelvin wave has been travelling for months. It left the western Pacific loaded with heat, carrying temperature anomalies 6 to 7 degrees above normal at depths between 300 and 800 feet. It moved east along the equator at a few miles per hour, invisible from the surface, detectable only through a network of deep ocean sensors. By early April 2026, it was passing east of the international date line. By mid-May, it was approaching the coast of South America. When it arrives, a specific physical process begins. Off the coasts of Ecuador and Peru, cold water normally rises from the deep ocean to replace warm surface water that gets pushed westward by the trade winds. This upwelling keeps the eastern Pacific cool, supports one of the world's richest fisheries, and maintains the temperature gradient that the global atmosphere depends on to distribute rainfall predictably. When the Kelvin wave reaches the surface in this region, it inserts a layer of warm water beneath the cold surface. The upwelling cold water can no longer reach the surface. It gets blocked by the arriving warmth. Sea surface temperatures in the eastern Pacific begin to spike. The Niño 3.4 index, the official El Niño thermometer, starts climbing. This is the physical moment El Niño officially begins. The temperature anomaly that forecasters have been projecting in models, the number that NOAA attached an 82% probability to, becomes a measured reality in the ocean off South America. The consequences in that region are immediate and severe. Coastal fisheries collapse because the cold, nutrient-rich upwelling that sustains them disappears. Anchovies, sardines, and the larger species that feed on them move to deeper water or migrate away from the coast. Peru's fishing industry, one of the largest in the world by volume, suffers dramatic losses within months of El Niño establishing itself. Communities along the Peruvian and Ecuadorian coast have historical memory of what strong El Niño events bring. Heavy rainfall in a desert landscape creates flooding on a scale the infrastructure cannot manage. Rivers that are dry most of the year fill beyond capacity. Flash floods carry sediment and debris into coastal towns. The agriculture that sustains those communities fails simultaneously as flood and drought alternate across different elevations of the same coastal region. The 1997 to 1998 event, which had a Kelvin wave comparable in many ways to what's moving through the Pacific in 2026, produced flooding in Peru and Ecuador that killed over 2,000 people and caused damage comparable to $8 billion in today's value. As of mid-May 2026, the surface expression of the arriving Kelvin wave was already visible in sensor data. The Niño 3.4 index was climbing toward the official threshold. Forecasters described the pattern as accelerating faster than most models had projected even a month earlier. The Pacific was not the only thing bearing witness to this transformation. Below the surface of the ocean, something else was registering the change. Something that has already been suffering for 3 years and may be approaching a threshold from which recovery is no longer possible. Beneath the surface of the tropical Pacific, a quiet catastrophe has been unfolding since 2023. Coral reefs cover less than 1% of the ocean floor. They support roughly 25% of all marine species. They protect coastlines from wave erosion, sustaining shorelines that millions of people live on. They generate tourism economies worth hundreds of billions of dollars annually, and they are exquisitely sensitive to temperature. A rise of just 1 to 2 degrees Celsius above a reef's normal summer maximum, held for several weeks, triggers bleaching. The coral expels the microscopic algae living inside its tissue, the algae that give it colour and provide up to 90% of its energy. Without those algae, the coral turns white. It's still alive, but barely. If temperatures drop soon enough, the algae can return. If temperatures stay elevated, the coral starves and dies. In early 2023, ocean temperatures began climbing toward bleaching thresholds across the Pacific, Indian and Atlantic Oceans simultaneously. The fourth global coral bleaching event began. It has not stopped. A study published in February 2026, analysing data from more than 15,000 reefs worldwide, found that 51% of the world's coral reefs had experienced moderate or worse bleaching since the event began. 15% had experienced significant mortality, meaning the coral tissue died and the reef structure itself began to erode. 51%. More than half of every reef system on Earth. In a single ongoing event. Scientists who study bleaching thresholds have warned for years that reefs that survive one major bleaching event need at least a decade to fully recover before they can withstand another one. The 2023 to 2024 El Niño drove temperatures to bleaching levels across the Pacific. Those reefs never had a year to begin recovery before 2026 began running near record ocean temperatures. If El Niño strengthens through 2026 and pushes ocean temperatures above bleaching thresholds again, in the same reef systems that were hit in 2023 and 2024, a significant portion of those reefs won't survive the second hit. Scientists at research institutions studying Pacific reef systems have stated plainly that certain regional reef communities could cross a point of irreversible collapse in 2026 if another major heating event occurs. Irreversible means the coral tissue dies faster than new coral can grow. The reef structure erodes. The ecosystem built around it over thousands of years collapses within years or decades. For coastal communities, reef loss translates directly into coastline erosion, increased wave damage during storms, and loss of the fish populations that healthy reefs support. Reefs are physical infrastructure. Their disappearance leaves coastlines exposed. The coral crisis isn't a future risk. It's active, it's measurable, and the ocean conditions building in the Pacific in 2026 represent exactly the kind of sustained thermal stress that pushes weakened reefs past the point of return. The damage isn't only visible on coral. Above the surface, in the open ocean and along coastlines, the warming Pacific is already killing things that communities have depended on for generations. January the 2026. The El Niño hadn't officially started, the big storms hadn't formed, the forecasts hadn't been issued, and fish were dying in Tonga. Ocean temperatures around the island nation of Tonga were running 3 to 4 degrees above normal. 3 to 4 degrees in open ocean water is a thermal shock on par with what bleaches coral. Fish that have lived in those waters for generations, calibrated by evolution to a specific temperature range, were encountering water their bodies weren't designed to handle. The deaths were documented, mass mortalities, species found floating at the surface in numbers that local fishermen described as unlike anything they had seen in their lifetimes. For Tonga, Fiji, and the surrounding Pacific Island nations, fishing is the foundation of the food supply. These are not communities with extensive agriculture or supply chain alternatives. The ocean provides protein for daily meals, income for fishing families, and export revenue for national economies. When the ocean heats beyond the tolerance of the species that live in it, that foundation cracks. The Tonga fish deaths in January 2026 occurred during what was technically still a La Niña period, before El Niño had even declared. The ocean was producing mass mortality events before the warmer system it was tilting toward had fully engaged. The same warming pattern affecting Tonga was showing up across the Pacific island world. Fiji's ocean temperatures were 2 to 3 degrees above normal in January. NOAA's Coral Reef Watch declared strong to severe marine heatwave conditions across the entire region. The Pacific Island nations, communities that produce negligible amounts of greenhouse gas emissions and bear minimal responsibility for the changes happening to their ocean, were experiencing the consequences first and most severely. Climate projections for Pacific fisheries extend the concern beyond 2026. Research projecting conditions to 2050 found that Philippine marine fisheries alone could face up to a 25% decline in harvest if ocean warming continues at current rates. Mackerel and large open water species face potential local collapse or severe population reduction in regions where they currently provide the primary food source for coastal communities. The disappearance of fisheries from warming Pacific waters wouldn't be a slow, manageable transition. It would arrive as sudden collapse when temperatures cross specific thresholds that trigger species migration or mass die-offs. Communities that have built their food systems around those species over generations would face abrupt loss of their primary protein source, with little warning and few alternatives. And the marine warming that's collapsing fisheries in the tropical Pacific is not confined to distant island waters. The same thermal anomalies are showing up along coastlines that most Americans consider well outside any climate impact zone. Off the coasts of California and Oregon, a marine heat wave has been building since mid-2025. Water temperatures along the American west coast are running 3 to 4 degrees Fahrenheit above normal. For an ocean that rarely sees dramatic temperature swings, that's a significant departure. It's not a short-term anomaly. It's been sustained for nearly a year and is continuing to intensify as El Niño develops in the deeper Pacific. The consequences are already visible. Salmon are dying. Pacific salmon species migrate through coastal waters at specific times of year, relying on cold, oxygen-rich upwelling to sustain them. When those cold waters warm significantly, salmon survival rates drop. Juveniles fail to make it to the ocean. Adults that do reach open water find their food sources diminished because the fish and invertebrates salmon eat are also stressed by warm water. Commercial salmon fishing along the west coast was already severely restricted heading into 2026. The marine heatwave is making the situation worse. Harmful algal blooms are expanding. Warmer water provides ideal growing conditions for certain toxic algae species that produce chemicals dangerous to marine mammals and humans. When those blooms reach shellfish beds, the shellfish absorb the toxins and become unsafe to eat. Shellfish fisheries from Washington state to California have been experiencing closures triggered by algal bloom contamination. Commercial oyster and clam industries are taking substantial economic losses. Sea lions and dolphins are dying in unusual numbers along the California coast. Rescue organizations have reported strandings at elevated rates throughout late 2025 and into 2026. The animals are starving because their prey species have moved or collapsed under the pressure of warm, low-oxygen water. Emaciated sea lions washing up on beaches aren't just an ecological tragedy. They are a measurable signal that the food web in that ocean is under severe stress. The West Coast marine heatwave set a specific record on September 9th, 2025, when the Northeast Pacific reached its highest average temperature ever recorded, 20.6 degrees Celsius, which is 69 degrees Fahrenheit, for a region of ocean that size. These numbers matter beyond their ecological consequences. A warmer nearshore ocean affects coastal atmospheric moisture, contributes to fog pattern changes, and alters the conditions under which fire weather develops. California's coastline sits at the edge of a region already experiencing intensified fire seasons. The relationship between marine conditions and inland fire risk is an active area of research, and the 2026 heatwave conditions are extending into the highest concern period of the year. The marine heatwave along the west coast is the local, visible version of the same planetary process driving everything in this story. The Pacific is warming. It's warming on the surface, beneath the surface, at the equator, along the coastlines, and in the depths. All of that accumulated heat translates into something that climate scientists use to measure an entire storm season with a single number. That number is being watched closely in 2026. Because if it reaches a specific threshold, it would confirm that this year produced more total destructive storm energy than any North Pacific season in recorded history. There is a number that captures the full power of an entire storm season in a single figure. It's called accumulated cyclone energy. Scientists calculate it by combining the wind speeds of every tropical storm across a full season, measured every 6 hours, and adding them all together. The result reflects both how many storms formed and how intense they were for how long. A season with many weak, short-lived storms produces a low number. A season with fewer but extremely powerful storms produces a much higher one. The West Pacific record for accumulated cyclone energy in a single season belongs to 1997,571 units. That was the year of the last comparable Super El Nino. That season produced storms that devastated the Philippines, Japan, and the surrounding Pacific Island nations at extraordinary frequency and intensity. By mid-May 2026, Sinlaku alone had contributed 40.6 accumulated cyclone energy units. One storm, in April, before the season had formally peaked. To understand what that means, consider that an average full Northwest Pacific season produces a total somewhere around 300 units. Sinlaku, a single April storm, delivered more than 13% of an average full season's energy output before peak season even began. If 2026 delivers 18 typhoons at above average intensity, as tropical storm risk has projected, and if those storms develop during an ocean temperature environment significantly warmer than 1997's baseline, the math points toward a season that could challenge the all-time record. Climate Impact Company stated explicitly in April 2026 that 2026 could set a North Pacific record for accumulated cyclone energy, when both the Northwest and Eastern Pacific basins are combined. The Eastern Pacific, as discussed, is also tracking toward an above-normal season. Combining both basins' outputs means the full extent of 2026's storm energy would be measured against a broader historical record, one that captures the full destructive output of the Pacific system on both sides. This is classified as a theory by forecasters, not a confirmed outcome. It depends on whether El Niño reaches strong or super status, whether it arrives early enough to fuel the peak of the season, and whether storm tracks deliver that energy onto populated coastlines or into open ocean. A record accumulated cyclone energy season that stays over open water is a statistic. A record season that makes repeated landfall is a humanitarian catastrophe. The distribution of that energy matters as much as the total. What makes 2026 particularly concerning is a combination of factors that goes beyond storm frequency and intensity. There's a detail sitting in the background of 2026's ocean warming story that most people have never heard mentioned in connection with tropical cyclones or marine heat waves. It involves an environmental regulation, a fleet of cargo ships, and an accidental consequence that no one planned for. In 2020, an international maritime regulation came into effect. The rule required that cargo ships burning heavy fuel oil reduce the sulfur content of that fuel dramatically. The goal was clean air. Sulfur emissions from ships had been linked to respiratory disease in coastal communities worldwide. The regulation was a genuine environmental success. Air quality improved, health outcomes improved, and then scientists noticed something unexpected happening in the ocean. Burning high sulfur fuel produces sulfur dioxide particles that release into the atmosphere. Those particles seed the formation of low-level clouds over the ocean. Those clouds reflect incoming sunlight back into space before it reaches the ocean surface. They function as an accidental sunscreen, reducing the amount of solar energy heating the ocean beneath major shipping lanes. When ships switched to low-sulfur fuel, those cloud-seeding particles disappeared. The accidental sunscreen evaporated. More sunlight reached the ocean surface. Researchers estimated the effect added up to approximately 0.15 degrees Celsius of additional localized ocean warming along major shipping routes in the tropical ocean. 0.15 degrees sounds minor. Applied to an ocean already running at near-record temperatures, already being pushed toward bleaching thresholds that are measured in tenths of a degree, it is relevant. The regions most affected by the disappearance of ship trail cooling site in the tropical Atlantic and Pacific, overlapping significantly with coral reef regions and the zones where tropical cyclones develop and intensify. Scientists monitoring the fourth global coral bleaching event have specifically flagged the sulfur regulation as a contributing factor to the extraordinary extent of bleaching observed since 2023. Reefs sitting in shipping lane regions may have experienced more thermal stress than they would have under the previous fuel regime. This is an example of how managing one planetary problem can create unintended consequences in another. The sulfur regulation was the right choice for human health. The climate consequences of that choice were real but unplanned. Understanding them doesn't mean the regulation was wrong. It means the systems involved are more interconnected than any single policy can fully anticipate. For 2026, the practical takeaway is that ocean temperatures are being pushed by multiple, overlapping forces simultaneously. Long-term climate change, El Niño. The removal of an accidental cooling mechanism, each one contributing a fraction of a degree. Each fraction of a degree expanding the zone where rapid intensification is possible, raising the thermal floor above which reefs struggle to survive, and pushing the global average temperature toward the threshold of another record year. If the El Niño that's building continues to strengthen through the rest of 2026, the combination of all of those forces could produce an outcome that goes beyond anything in the instrumental record. An outcome not just for storm seasons or reef systems, but for the global temperature average itself. The possibility that 2026, or the year that follows it, becomes the hottest in human history is being discussed by climate scientists with a seriousness that should command attention. 2024 was the hottest year ever recorded in human history. It broke the record set by 2023, which broke the record set by 2016, which broke the record set by 2015. Each of those record years was either during or immediately following a significant El Niño event. The pattern is consistent. El Niño pumps heat from the deep ocean into the atmosphere. Global average temperatures spike during the event and reach their peak in the year or two following it, as the atmosphere finishes absorbing the released heat. The record usually doesn't come during the El Niño itself. It comes after. This means that even if 2026's El Niño peaks in late 2026, the atmospheric temperature record might not fall until 2027. Forecasters, including those at the European Centre for Medium-Range Weather Forecasts, have stated this explicitly. Samantha Burgess noted in May 2026 that ocean temperatures were days from breaking all-time monthly records again, and that conditions were tracking toward what could make 2026 or 2027 the new hottest year in recorded history. The key variable is whether a super El Niño materializes. A strong El Niño in 2026 would push global temperatures significantly above 2024's record. A super El Niño, the 1 in 3 possibility as of mid-May, would push further. Combined with the already elevated baseline from the decade of warming that preceded it, a 2026 super El Niño would be operating in a thermal environment that no previous event has encountered. The global average temperature record isn't just a statistic. It maps directly onto outcomes across the physical world. Each tenth of a degree of additional global warming expands the geographic zone where rapid intensification is possible. Each tenth of a degree pushes more coral reefs past bleaching thresholds. Each tenth of a degree increases the moisture content of the atmosphere above storm systems, producing more rainfall during landfall events. For a 15-year-old listening to this, the number that matters most is simple. The year you were born, the global average temperature was already above the baseline that scientists use to define normal. Each year since then has been warmer, and 2026 sits at the edge of what might become a new ceiling, one that every subsequent year will be measured against. The honest picture of what comes next is exactly what forecasters are struggling with. The signals are the strongest ever seen at this point in the year. The spring predictability barrier means the full strength of the event won't be confirmed until autumn. The models are aligned but not unanimous. What the next 6 months will reveal, and what they mean for every coastline facing the Pacific, is the question that ties everything in this story together. Every forecast mentioned in this story carries a confidence level, and every one of those confidence levels has a limit. It's worth being clear about where the certainty ends and the genuine unknowns begin, not because the situation is less alarming than described, but because honest uncertainty is part of how science works, and understanding it matters for what comes next. What is confirmed? The Pacific is running at near record temperatures. The subsurface Kelvin wave has been the strongest of its type on record. Trade winds have been weakening. El Niño is developing with 82% probability of declaration by July. The sea surface temperature trends are confirmed by multiple independent monitoring systems. Sinlaku's destructive landfall on Saipan is documented fact. Coral bleaching affecting 51% of world reefs is confirmed by analysis of 15,000 reef sites. What is a strong theory? The 2026 typhoon season becoming the most active since 2015, potentially challenging the ACE record. This is supported by the confirmed ocean conditions and the forecasting track record of tropical storm risk in the European Centre, but depends on sustained El Niño development through peak season. What remains genuinely unknown, whether a super El Niño materializes. The 1 in 3 probability is the scientific community's best estimate based on current data, but the spring predictability barrier is real. NOAA's Emily Becker stated directly that models tend to overestimate El Niño strength when forecasting from spring. Australia's Bureau of Meteorology maintained that a neutral outcome remained possible, though increasingly unlikely. The 2014 false alarm is instructive. A powerful Kelvin wave in 2014 produced confident forecasts of a major El Niño. The event that developed was moderate. The setup in 2026 is stronger in key indicators than 2014's was, particularly in subsurface heat content and surface temperature anomalies. But the precedent for overforecast exists. What also remains genuinely unknown, exactly how 2026 conditions will translate into specific storm tracks. A record warm ocean can produce more intense storms, but whether those storms make landfall in populated areas or track over open ocean is partly chaotic. The Philippines experiences roughly 20 systems per year. In a super El Niño year, Intensity increases, but landfall frequency can actually decrease for some regions while increasing for others. The ACE record possibility, the potential for 2026 or 2027 to be the hottest year in history, and the storm track anomalies threatening California and Hawaii are all well-grounded theories. They are supported by the confirmed data. They are not guaranteed outcomes. What's not uncertain is that the ocean is loaded with energy. The storm season is beginning in conditions unlike any previous season in the record, and the precursors that were present before every major El Niño in history are present now. The models disagree on degree. They agree on direction. The next 6 months will replace these probabilities with measurements. El Niño will either declare or fail, storm intensity will either match or exceed the forecasts, ocean temperatures will either set new records or fall just short. Every measurement made between now and December 2026 will either confirm or revise what scientists currently believe about the Pacific, and for every community facing that ocean, the question isn't what the models say, it's what the next 6 months actually deliver. The Eastern Pacific hurricane season opened today, May 15th, 2026. The Northwest Pacific has already produced one of the most powerful early-season typhoons in the modern record. The Kelvin wave is surfacing in the Eastern Pacific. El Niño is declaring. The ocean is at temperatures that have no direct historical comparison at this point in the year. Between now and December, the Pacific will deliver its verdict. June and July will show whether El Niño crosses the official threshold and how quickly it intensifies after declaration. July and August will show whether peak season typhoon development matches or exceeds the 18-storm projection from tropical storm risk. August through October will determine whether the season produces accumulated cyclone energy approaching the 1997 benchmark. September through November will reveal whether El Niño reaches strong classification at 66% probability or Super El Niño status at 33%. Each of those milestones will arrive as a measurement, not a projection. The spring predictability barrier will have passed. The models will be replaced by actual sensor readings from buoys across the Pacific, actual storm data from satellites, and actual atmospheric readings from weather balloons launched into the systems themselves. For the Philippines, the window matters in terms of preparation time. 9 to 17 tropical cyclones entering Philippine waters means an average of 1 or 2 per month during the peak season window. Emergency management, evacuation planning, and storm shelter capacity need to be scaled to the upper end of that range. For Japan and Taiwan, which sit in the recurvature zone where mature Northwest Pacific typhoons turn northward and make landfall, the coming months represent a period of elevated risk unlike recent seasons. For Hawaii and the American West Coast, the question is whether El Niño's documented tendency to shift Eastern Pacific storm tracks northward produces major flooding events in regions that have limited infrastructure for tropical moisture. For coral reefs across the Pacific, the window is even more urgent. Reefs already weakened by 3 years of continuous bleaching face the possibility of another heat pulse during the El Niño peak. Some will not survive a second consecutive hit. For the global temperature record, the atmosphere is still absorbing the heat released by a near-record ocean. Whether that absorption pushes 2026 or 2027 past 2024's record depends heavily on how strong El Niño gets and how long it persists. The story of the Pacific in 2026 is still being written. The opening chapters arrived with Sinlaku's landfall in April. The middle chapters are being written right now as the Kelvin wave surfaces and El Niño takes hold. The final chapters will be read by communities across the Pacific coastlines of the world in real time as the storms arrive. The ocean has been loading energy for years. The systems that release that energy are organizing. The window for maximum impact runs from now through the end of the year, and the next storm is already forming somewhere out there, over water warmer than any season in recorded history has ever seen.